Okay, so hi everyone. Welcome to our IA seminar series. It's a pleasure to have today with us Rocco Lico. With Rocco, we know each other since a very long time. We started together our path into astronomy since the Faculty of Astronomy at the University of Bologna, back then in some remote year, better not to say. And then, interesting enough, actually, our path crossed several times, switching institute and etc. In fact, Rocco got his PhD from the University of Bologna in 2015. And then he moved for his first postdoctoral appointment at the Max Planck Institute for Radio Astronomy in Bonn, where we meet each other again. And then he moved to Granada, where he spent 3 years as a Severo Ochoa postdoctoral fellow at the Institute of Astrophysics of Andalusia in Granada. And after that, he returned to Bologna, where he is currently a staff researcher at IRA-INAF, the Institute of Radio Astronomy in Bologna. So Rocco's research mostly focused on active galaxies, supermassive black hole, and their relativistic jet, and mostly using the very long baseline interferometry techniques. Rocco, in fact, is also an active member of the EHT collaboration. But very recently, he also expanded his work, moving toward the galactic neighborhood and using high-resolution observation to study galactic transient. And today, in fact, he will present a talk entitled Capturing the Real-Time Expansion and Evolution of Symbiotic Novae. So thanks for being with us. Thanks for accepting our invitation, and the floor is yours.
Thank you very much, Carolina, for the introduction, and thank you very much for the invitation. Next time I'll really try to be there in person. That would be great. And as Carolina mentioned, I'm pretty new to this topic. I started a couple of years ago working with Novae, and I'll try to let you know what I've learned in these years. So in case there is any expert in the room, please bear with me. I will start with a pretty general introduction on Novae. They are astrophysical transient events produced by thermonuclear explosion on the surface of a white dwarf in a binary system with a companion star that could either be a main sequence star or a red giant in a semi-detached binary system, which means that the companion star completely filled its Roche lobe, and the system is in a state of mass transfer equilibrium, where hydrogen-rich material is being transferred, from the companion to the white dwarf through the L1 Lagrangian points, being pulled by the white dwarf's gravity. And due to the conservation of the angular momentum, this gas doesn't fall straight down, but it curves and forms an accretion disk around the white dwarf, and then this material accumulates on the surface of the white dwarf until a critical limit for pressure and temperature is reached at the base of this accreted shell on the surface of the white dwarf, and then a thermonuclear explosion is triggered, and as a consequence, the whole white dwarf envelope, external envelope, is ejected into the surrounding circumbinary medium at high speeds. It's around, few thousands of kilometers per second, and produce this sudden increase in brightness that we observe as a nova event. And then as this shell expands and propagates, it interacts with the companion star wind, creating and the circumbinary medium, creating astrophysical shocks that then, consequently accelerate particles and produce emission across the whole electromagnetic spectrum. And after the nova event occurs, the whole system is not totally disrupted, but the accretion and the matter transfer starts again. The accretion disk forms again, and then at some point the explosion is triggered again, on different time scales. I'm going to show a slide about this during the talk. And I mentioned that the companion star could either be a main sequence star or a subgiant. In this case, it's a classical nova event is called, or a red giant. In this case, is called symbiotic nova. So when we have a main sequence star, these systems are usually called cataclysmic variables, while for symbiotic nova, it's called symbiotic star systems. And they have different properties. Usually cataclysmic variables are tight systems with binary separations of a few solar radii. And in the case of symbiotic stars, they are wider with orbital binary separations of the order of a few astronomical units. And this is reflected then into the orbital period as well. So in the case of classical novae, the orbital period is from hours to days, while for symbiotic novae is from months to decades. And another important difference is in the way the mass is being transferred. So here are a couple of sketches for the classical novae to the left and for symbiotic novae to the right. So in the case of the classical nova, as you see here in this very schematic representation, maybe not extremely precise, but you see the main sequence star are filled entirely the Roche lobe and is transferring mass through the L1 Lagrangian point. And then an accretion disk forms around the white dwarf. And this is, a pretty efficient way to transfer mass. While in the case of symbiotic novae, the red giant has this pretty strong and dense wind, and part of this wind is being intercepted by the white dwarf and accretes on the surface of the white dwarf. This doesn't look like a very efficient way, to transfer mass because the wind is going in no direction and only a small part is being intercepted by the white dwarf. But this is still enough to trigger the thermonuclear reaction and explosion on the surface of the white dwarf. And here is how nova remnant looks like. This is the famous GK Persei nova. This is a nova that exploded back in 1901, so more than a century ago. And when it appeared as the brightest star in the sky for a few days, and then it gradually faded away. And in this image, we see several features. We see this bright central region, plus some gas clumps, this kind of orangish sparks that emanates from the central point, which resemble kind of fireworks, pink. And it expands in pretty much spherical fashion. Of course, this is not the case for all the Novae explosions and remnants, as we are going to see now in a minute in the next slides. And this image is a composite of images from taken at several frequencies. This is a composite image from X-rays observed with Chandra during a decade, more or less from 2000 to 2013. This is after one century, more or less, after the explosion. And then we have the optical data from Hubble Space Telescope in yellow orangish, and then the radio data from the Jansky Very Large Array in pink. Here you can see better the three components I mentioned, and you see how the X-rays trace the emission from the hot gas. The optical data shows these clumps of material that were ejected during the nova explosion, and the radio data, probe the shock propagation. So they reveal the emission from these electrons being accelerated up to relativistic speeds. And as I mentioned before, after this explosion occurs, then the system, the whole thing starts again, and the life cycle starts again. And the recurrence frequency depends mostly on two factors. One is how efficient is the mass transfer from the companion to the white dwarf, which is represented here in the y-axis, and how massive is the white dwarf, that is here in the x-axis. And this is a work from Kato et al. 2014, and you see how they obtained these recurrence times indicated here on these solid lines, that they depends on these two parameters, and they could be range from millions of years to a few years to the top right. And you see how, for instance, for a given mass for the white dwarf, the recurrence period is shorter, of course, for higher accretion rates. And on the other end, for a given accretion rate, the recurrence period is shorter for larger white dwarf masses. And if we focus on the upper right part here, where we have this recurrence time of a few years, when nova recur on human time scales, we call this nova recurrent nova. I mean, it's such that we have more than one, we can observe more than one explosion during a lifetime. And I put together all the known recurrent novae here in this slide, and you see there are in total 11 so far known recurrent novae. So just to give you some numbers, in the case of the classical novae, for instance, the known recurrent novae are around a few hundreds. I mean, more than 400 classical novae are known, and among them, only 6 of them are considered recurrence, in the sense, that at least we observed 2 explosions in, over a lifetime. And in the case of symbiotic novae, only 5 of them are recurrent, and they are listed here. And the fact that these targets, these 11 targets, are here in this slide, in this table, that means that they have efficient mass transfer and that they have a pretty massive white dwarf with a mass pretty much close to the Chandrasekhar limit. Otherwise, a lower mass for the white dwarf would require much more fuel to reach the ignition pressure, and this pushes the recurrence time to thousands of years. And this is also the reason why the recurrent novae are considered good candidates as potential progenitors of supernovae 1a, and that's why they are, pretty important. And what I want to do now is to focus on some remarkable sources from this list. I mean, all of them are already remarkable for being in this list, but some of them are even more remarkable and fundamental for Novae science. Let's start with this called VU 407 Cygni. This is symbiotic recurrent nova with a Mira star companion. The Mira star is a pulsating late-stage red giant that provides, a massive amount of fuel with a very dense wind in which the shock is propagating. It's located at a distance of more or less 3.5 kiloparsec, and as an orbital period, of around 43 years, with a orbital separation of between 15 and 20 astronomical units, which make it, the widest of all the recurrent systems. And the last eruption was observed in 2010. This was, a very crucial moment because during this eruption, this was the very first time that a nova was ever been detected at gamma rays. And you see here the detection map to the right. This is the Fermi detection map between 200 MeV and 100 GeV. And this was really the first time that this provides, clear evidence that shocks in nova ejecta can accelerate particles up to relativistic energies. I mean, before 2010, we used to think of novae as mostly thermal events, mostly, emitting hot gas. Nobody did really expect that they can produce such high energy gamma rays. And this changed the whole theoretical framework. And such gamma rays can be produced at least by two mechanisms that we know. First, the hadronic processes, which are proton-proton collisions, where the gamma rays are produced via pion decay, resulting from proton-proton collisions between the fast-moving ejecta and the slower Mira wind, the slower dense wind. The other processes are the leptonic processes, which are electron-proton interactions, where relativistic electrons upscatter low-energy seed photons up to GeV energies via the inverse Compton scattering. And here to the right, to the bottom right, you see this average Fermi gamma ray spectrum above 100 MeV, and you see both the best fit lines for hadronic and leptonic models, the dashed and the solid lines. And as you see, both of them, they fit pretty well, the spectrum, although usually the hadronic models are favorites in this case because, the dense Mira wind naturally provides stationary target protons for the expanding shock, and so with the production of gamma rays. All right, now let's go back to our list. And let's take another one of these remarkable sources. Let's talk now on RS Ophiuchi. This is really the archetypal symbiotic recurrent nova with a recurrence time of around 15-20 years. So we have at least 7 recorded outbursts, and this makes this target really our most reliable laboratory. And we were able to track the shock evolution over more than a century for this target, as you can see. And this is the reason why RS Ophiuchi is considered like the gold standard for studying shock physics in real time. And this target is at 2.7 kiloparsec distance from Earth, and with an orbital separation of 1.5 astronomical units. And here I'm showing the historical visible magnitude light curve that I plotted from this online tool from the American Association of Variable Star Observers, which is, a nice database containing photometric magnitude estimates for more than 200 novae, and this is mostly provided by amateur astronomers. So it's a very interesting tool if you are interested in that. And as you can see from this light curve, so that dates back to 1933, and we see some obvious outbursts in these spikes that you see here, with the oldest one dating back to 1933 and the most recent one to 2021. But then if we take a look at other archival data, we can infer other explosions dating back to 1898 and 1907, plus another one around 1945, which was most likely missed because the source was too close to the sun. And this was also, during the Second World War, so maybe it was just missed events. And now let's focus to the most recent one, which is this one from August 8, 2001. And this is a zoom of this peak in the previous light curve. So this is the light curve around this last event. And you see it has pretty interesting features. So we see some small oscillations around magnitude 11, starting a few months before the explosion. And then, there is this rapid increase from magnitude 11 to magnitude 4.3, more or less in around 1 day. That's incredible. And then it decays on time scales of a few months, so on much longer time scales. And it goes back to the pre-outburst magnitude, more or less, around 3 months after the outburst itself. And then there is this hole in the light curve that you see here, and this is because the source was too close to the sun for being revealed. Among the other things that I mentioned that makes this target, exceptional, for this very last event, another thing that make it a remarkable event is that this was the first time a nova was observed at very high energies, above 100 GeV, by the HESS telescope. There is this 5-element Cherenkov telescope in Namibia, here to the top right, and the detection map between 100 GeV and 100 TeV is here to the bottom left. And to the right, I'm reporting here the gamma ray light curves. That includes both data from HESS in red and the data from Fermi in this bluish. And you see the similarity between the spectra of the Fermi and HESS data and their similar decay profiles. They indicate, a common origin for the emission at these two frequencies. And now we know, that high energy emission is produced, that there are strong shocks accelerating particles. If we want, to image these innermost regions and see the dynamics of these propagating shocks, the only way we can do it, the only tool we can use to do it, is by means of very long baseline interferometry. So for those who are not familiar, VLBI the VLBI technique consists in synchronizing signals from multiple radio telescopes by using precise, atomic clocks. And by combining these signals, the whole array simulates a single big virtual telescope with a diameter that is of the order of the maximum distance between the antennas. And then you understand that when we place the stations across different continents, with this technique, we can create an instrument really as large as Earth, the Earth itself. And this provides us with the highest angular resolution currently achievable in astronomy. And for this specific case, we used one of these big arrays. This is the European VLBI network, as you see here to the right, this image to the right. There is a network of radio telescopes primarily located in Europe and Asia, with some additional antennas in Puerto Rico and South Africa. And currently, is the most sensitive VLBI array in the world. And what we did was to monitor the expansion, the source, starting from 2 weeks after the outburst up to 2 months. And we have 4 epochs. We did this at 5 and 1.6 gigahertz. And as you can see, in some epochs, we also had the eMerlin join the EVN. The eMerlin is another small array of 7 radio telescopes located over more than 200 kilometers, across Great Britain. And here are the main results we obtained from this campaign. So to the top row, we have the images for the 4 epochs at 5 gigahertz, and to the bottom row, the images at 1.6 gigahertz. The time after the outburst is indicated to the top right in each frame here, and you see the first one is 2 weeks after the outburst, then we have 24 days, 34 days, and 64 days after the outburst. And this was really the first time observing a nova event with such level of details. And something that really made the difference in this case, was really a game changer, was the fact that after this last event, we had the very precise position of the binary provided by Gaia, by the third data release. And indeed, all these images are centered to the Gaia position. And we can see this evolving elongated source structure that can be represented by three main components: compact and bright central region, and then these two expanding lobes in east-west direction on opposite sides, from the central binary that is perpendicular to the orbital plane. And a remarkable feature we find here is this flux density decrease that we observe between the eastern lobe and the rest of the source. That is produced by the absorption from ionized gas, and this is called this density depression is this brightness depression is called density enhancement on the orbital plane, DOP. Basically, what happens is that the gravitational pull of the white dwarf is channeling most of the mass lost by the red giant through its wind towards the orbital plane and forms, this density enhancement. And then the combined effect of this density enhancement together with the presence of the accretion disk is to confine the expelled material within these two bipolar structure rather than, a spherical expansion as we have seen in the other case. And if we look at the two lobes, the one to the west, it's pretty much circular, while the one to the east, it's more arc-like structured. And this is because this represents the outer edge of the eastern lobe as it emerges behind this density enhancement. And then the first epoch, this is also very important, is interpreted in terms of the western lobe that is propagating towards us, with the binary, the central binary, in the background, and then the whole eastern lobe fully obscured, absorbed by the DOP. And then, it pops up as it reaches a certain projected distance from the central binary, where the optical depth is dropping down. Anyway, these images are very, very rich of information, but I will move on. And this is more fancy representation of what I just said, with the binary system located at the center of this sketch. And then you see the gravitational pull of the white dwarf channels most of the mass lost by the red giant towards the orbital plane in this whitish area. And then this explosion generates the shocks that propagate in opposite directions. And then as they propagate, they heat up the circumbinary medium and the red giant wind to up to 1,000,000 degrees, producing X-rays and thermal red emission. And then these shock waves also accelerate the electrons, both electrons to relativistic speeds, producing radio synchrotron emission, and protons to relativistic speeds, producing the gamma rays with the mechanisms that I mentioned before. And this is an animation made out of the four images at 5 gigahertz that I've shown before. And here in this GIF, you can see, you can appreciate better the expansion of the two lobes. And what we can do by considering the distance of the lobes of the external edge of the lobes from the central binary at different epochs is that we can obtain the expansion velocity as well, the expansion speed as well. And you see this in the left plot, where we find basically that lobes expand linearly with an average speed of around 7,000 kilometers per second with no significant deceleration. And this is indicating that density gradient perpendicular to the orbital plane is pretty steep. On the other hand, we saw that the two lobes are different in the sense that the western one was pretty spherical, the other one was like an arc, but this is only because of geometrical reasons, because of the absorption of the DOP. But if we assume intrinsic similarity and asymmetry and symmetry, between the two lobes, by considering the flux density ratios at different times and so at different distances, we can also estimate the density distribution along the DOP. And you see here in this plot, and if we integrate this across the whole volume of the DOP, we can obtain a total mass of the order of 4.3 per 10 to the minus 6 solar masses. And then if we take this value and we put this together with the estimate of the red giant mass loss rate, which is of the order of 10 to the minus 7 solar masses per year, together with the estimate of the white dwarf accretion rate that is estimated to be around 10 to the minus 8 solar masses per year from several, theoretical arguments. By putting all these numbers together, what we obtain is an important outcome, and is that the white dwarf likely is accreting around 1/10 of the whole mass lost by the red giant, with most of this mass going, to feed this density enhancement and then the circumbinary region. Another very important diagnostic tool is, of course, looking at the spectra. So here I'm showing some spectra, showing the spectral evolution of the Fuki after this most recent outburst. And these are spectra taken at several times after the outburst from 22 days, the upper blue line, up to 94 days, the orange line to the bottom after this 21st outburst. This is from Munari et al. 2021. And the most relevant emission lines here are indicated in red to the top. And this is very important because the evolution of the spectrum reflects the different stages of the expansion, because there are specific lines at each stage. So when we see certain lines, we know exactly in which stage of the evolution the system is. Now, before looking into the spectra, let me just say that during the quiescent phase, the spectrum usually is dominated by hydrogen-Balmer lines and helium-1 and 2 lines coming from the white dwarf accretion disk. These are, pretty narrow lines, double-peaked lines with one peak coming from the receding part of the disk and the other one coming from the approaching part of the disk, with typical speeds around 500 kilometers per second. And these lines are, powered by the accretion energy. After the outburst, in the early stages, as you see here in this blue line, and the lines are indicated here to the top in blue, these early phases are still dominated by hydrogen-Balmer lines and helium-1 and 2 lines. However, these are not coming anymore from the accretion disk white dwarf, that is the white dwarf accretion disk that is, completely swallowed by the explosion. But they are coming now from the expanding ejecta. And we know this because these lines are now much stronger and much broader. They are broadened by thousands now of kilometers per second, reflecting the kinetic energy of the explosion. Indeed, they are now powered by the thermonuclear energy. And then, moving on, after several weeks from the explosion, we start seeing additional lines. And as the shell expands and the density drops down, it becomes optically thin, and we now see into the cooler interior, and forbidden lines, marked now by these black boxes here and indicated in green to the top, starts to emerge. Lines like the oxygen-3 or the nitrogen-2 or the neon-3. And this originates from the entire volume of the ejected shell. And then at later stages, several months after the explosion, you see now they are indicated here in these red boxes, we have the so-called coronal lines. This phase appears when the shell is basically transparent, and we can see directly into the high velocity shock zones. And we see these forbidden transitions from highly ionized heavy elements like the iron 10 or the iron 14, and this requires temperatures of millions of Kelvin to strip all that many electrons, from the iron in this case. And this last phase, the coronal phase, is the shock signature. I mean, we know there is a shock there, and these lines originate at the front, at the shock front, where the fast-moving nova ejecta slams into the slower medium. Indeed, they are more prominent, such lines, in the symbiotic novae, where we have the more dense medium from the red giant, than in classical novae, where they are, pretty faint or almost absent. And then we know we are tracing the shock fronts from these lines, and we can combine this with the VLBI observations and we can image the shock front, and then we can really pinpoint the region from where these lines are coming from. That's why, in this case, VLBI is really a powerful tool. This is another of these very, very, very rich diagrams where we can talk half an hour. So let's move on. And this is a comparison of our results with the results from the previous explosion from 2006. And these are VLBI images obtained in C and L band in the two lines, left and right, at different epochs after the explosion, mostly similar to what we have 2 weeks. This is 14 days after, 21 days after, and 28 days after. And you see that the images are pretty similar to what we obtained. However, back then in 2006, they didn't have the astrometric position by Gaia, and so they didn't know exactly where the binary was located. Indeed, their interpretation was that this was a spherical expanding shell, the one to the right, with the binary at the center of this spherical shell. And then this eastern lobe was interpreted as a polar jet, leaving the central binary at much greater velocity than the spherical ejecta. But now we could give, the proper interpretation thanks to the Gaia accurate position and distance. That's why I mentioned that this was a game changer and was very important, because this structure was not interpreted anymore in terms of a spherical expansion, but this is now, these bipolar outflows. And the images I showed in that slide with the two frames at 5 gigahertz and 1.6 gigahertz, they were all convolved to the same resolution, just to make, an homogeneous comparison across the different epochs and for the different images. But if we look at, for instance, the first epoch, 5 gigahertz, in its full resolution obtained with the whole array, we see that the image is, much more interesting. It's not just a single blob, but it shows this more complex, elongated structure with this kind of granular-like morphology. These spots of enhanced brightness distributed more or less, mostly along the outer boundary of this region that is, roughly elliptical. And this is not really new, because if we look at some previous images from 2026, a similar structure was observed. You see similar granular-like structure here from O'Brien et al. 2008. And if we overplot this ellipse to our image, you see that more or less they fit. And this is very interesting, because this supports the idea that the way in which the wind from the red giant is refilling the circumstellar space, which has been emptied, by the previous explosion, it replicates in a self-similar way at each new event. And another interesting point is that a kind of granular structure was also invoked to explain some X-ray variability at much closer distance from the binary. And now we see that this kind of granularity is observed also at larger distances. And this is interesting to try to understand how these two things relate. And there are several ways to try to interpret this kind of granularity here, like they could be inhomogeneities in the expanding ejecta after the explosion. And, because of the turbulent nature itself of the shock, the propagating shock that is propagating through the pre-existing medium, that it could be clumpy itself. So, this is pretty natural to observe such kind of structures. And since we mentioned the X-rays, this is always regarding the most recent event, the X-ray light curve. To the top panel, this is in red for the 2021 event and in black for the 2026. And to the bottom, this is the hardness ratio, that basically is, the spectral slope that is telling us when the spectrum is dominated by high energy or low energy X-ray emissions. And you clearly see this is pretty interesting, because we have these two components. We have a first high energy component during the early stage, within days after the outburst. And this is coming from the shock that is expanding through the dense red giant wind, and involves temperatures of a few million Kelvin. And we have a second component that pops up weeks and months after the outburst, once the shell expands enough and becomes optically thin, and we can see again through the central binary. Indeed, this second component is coming from the residual nuclear burning on the white dwarf surface, involving a few 100,000 kelvins in terms of temperature. And the hard X-rays in this case are telling us information about the environment, about the wind density, while the soft X-rays of the second component are telling us information about the central engine, like the white dwarf mass and temperature. Okay, now let me conclude by picking up another very remarkable source from this, Novae, from this already very short list. This is considered to be the rock star among all the recurrent novae. This is the Corone Borealis. Maybe you already heard about this source. So the Corone Borealis is a symbiotic recurrent nova with a pretty massive white dwarf, and it's at a distance of 0.9 kiloparsec. I mean, this is really the closest. And it's also the brightest, because during the peak brightness, it reached magnitude 2. And the recurrence time is around 80 years, more or less, and the orbital separation is 0.5 astronomical units. And here to the right, you can see the light curve during the last explosion that was back in 1946. And you see, this is a pretty interesting light curve. It's very interesting with some interesting features, and that let's take a look at it. So you see that well, around 8-10 years before the outburst, the source is already as this enhanced mass transfer phase and has this pre-eruption high state, where this is also known as superactive accretion phase. And the white dwarf here is being force-fed a massive amount of fuel, pushing the surface layer toward the critical pressure that is needed for the thermonuclear runaway. And then around 1 year before the outburst, we have this dip in brightness, which is most likely due to a reconfiguration of the disk after this very enhanced and chaotic mass accretion in these past 10 years. And then we have the outburst that reached this magnitude 2. This, as I mentioned, is the brightest among all the current novae. The second one is the IRA-Ophiuchi, as we said before, that reaches 4.3 in magnitude. And then we have this final interesting feature, which is this secondary peak here in the light curve, which is due to a secondary outburst occurring well, in this case, it's around 3 months after the main outburst. And the very interesting thing here is that if we compare this light curve to the one of the previous eruption, which was back in 1866, I'm not showing it here, but if we compare them, they look identical. They are really identical. And then if we, in all the components, the pre-eruption high state, the pre-eruption dip, the secondary outburst, the peak magnitude during the eruption, everything is really identical. So we expect that even the following explosion should be identical. And if we make a very, very quick and easy math here, we find out that the next explosion should be exactly now, in this year, in 2026. Indeed, if we look at the light curve, the current light curve, you see that in 2015, T Corona Borealis already entered this pre-eruption high state that ended in 2023. And we are currently in the dip, and we are in this phase where the nova, should be already occurred. That's why the whole community is in a high alert state, because this could literally explode from one moment to another, and everyone is ready to observe and to monitor the source. And this is why this is considered the rock star of this among all of them, and this very important source and a unique target, because this is the only one that you can really predict. This is a really unique feature. While novae can explode from one moment to another, we know that this one is going to explode now because of these reasons. And then it's also the closest among all of them, and this means that we can really increase the resolution by using the same instrument we used for IRA-Ophiuchi. We can double the resolution, and so we can really dig into the innermost part. Anyway, that's why we are all very excited about this source, and I hope it's going to explode very, very soon. And this was my last slide, so I hope I conveyed to you the importance of studying novae for several reasons, for a big range of reasons. It's from the binary evolution to the mass transfer accretion physics, shock propagation and particle acceleration. They are potential progenitors of supernovae 1A, and I didn't mention that they are very important for the chemical enrichment of galaxies. Indeed, they are considered lithium factories. It was recently found that they are the primary source of lithium in the universe. Anyway, there are so many reasons, and I also hope I conveyed how important is, in this context, the use of VLBI that provide the necessary angular resolution to spatially resolve the complex geometries and of these expanding shocks. And that's it. I'm not going to mention about this, but of course, the square kilometer array will revolutionize the science, and we can do with novae, because, well, besides the increased sensitivity and resolution, it will allow us to move from just single target studies of a few well-known objects to a statistical significant population study, allowing regular observations multiple times in a year. So things will change a lot. And anyway, this is a chapter of the new white book, which was accepted yesterday and will be published soon. So in case you are interested, please take a look at it. And I will stop here. Thank you very much.
Thanks, Rocco. Very interesting indeed. You convinced me this that the galactic neighbor can also be interesting.
Yeah, yeah. It's closer, and real-time studies could be very
And
helpful.
some cool stuff is also happening there. Yes, you're right. You
Yeah.
convinced me. So, any question? You can unmute yourself, raise your hand, whatever you like.
Maybe I can ask something real quick.
Sure.
Um, as for this first binary that you showed,
Mhm.
um, I guess we had already a handle on like the orbital period, orbital separation, but was the when you did the VLBI observations of this expanding
Yes.
shock, was this a confirmation of the orbital orientation that we already knew, or did this even put better constraints maybe on what the orientation was of the orbit?
Yes, I mean, we could put much tighter, constraints on the orientation of the binary, on the separation, and especially, thanks to this flux depression we are observing here, we can really track the geometry of the orbital plane and understand how is this oriented, where is the binary located during the explosion, well, the companion with respect to the white dwarfs and many more things. Well, this is, of course, about only VLBI, but then there were many complementary studies by using spectroscopy, and then they inferred again. As we obtained, for instance, the expansion speed by just imaging the shock at different times, they were also extracted by just analyzing the spectral lines, and these speeds that they got were, very consistent with what we are getting here. And so we can not only confirm, but then also infer many more information on the actual geometry and physics of the evolving system.
Yes, that's very exciting. Thank you.
Thank you.
I take advantage. I don't see any other hand. I also have one question, maybe very stupid, about this. This system here, if I understood correctly, you inferred the density of along this orbital plane of the material on this orbital plane.
Yes, yes.
And then from that, you told us something like that the white dwarf is accreting something like 1/10 of the mass ejected by the red giant. Ah, yes, exactly.
Yes, yes.
So where does the rest of this mass goes, and why it doesn't contribute to the optical depth? Why is only the mass that cluster into this orbital plane that
Yes, that's a great question, actually, not silly. And this is very interesting because, I mean, if you remember at the beginning, I showed this sketch that I made, and I mean, although it might not be very precise, but if you look at the symbiotic Novae to the right, which is the case of Ares Ophiuchi, so the white dwarf is only intercepting a very small fraction of the whole mass lost by the red giants. So the fact that with these numbers we obtain that only 1/10 of this mass is being accreted, this makes totally sense, within this picture. And to answer to your question, where is this going? This is, I mean, most of the mass that is been lost is going into in circumbinary medium that is, pretty dense and makes the shock spectacular because of the interaction. And then the other amount that is there remaining is going into this density enhancement on the orbital plane that is, pulled by the gravitational pull of the white dwarf, which is taking this material and pulling this above the orbital plane.
Okay.
I mean, the picture is pretty consistent. That's why I was happy with these numbers, because this was, within the sketch that we have here and all the expectations.
Okay, so the
Yeah.
remaining kind of 90%, it makes this the environment more dense, and then it's what creates then this shock and particle acceleration.
Exactly. Exactly. Yeah.
Interesting.
Yeah.
Cool. The imaging, the VLBI imaging and images are
Yeah, that's
fantastic.
right. That was tough, but in the end, that was cool. Yeah. And the other interesting thing was, to interpret the first epoch, this blob, not at the expanding shell, but just the western lobe expanding towards us, and then everything is behind this, and the eastern lobe is totally hidden by the diop, by this density enhancement. Yeah, and we can do this because we have the Gaia position, and so we can properly interpret now.
Are you going to have do you have the Gaia position of the other Novae also that you expect?
Yes.
Okay, so you can do the same thing.
Yeah.
I've seen some message now, I don't know why, from Dima. Let us know when it explodes. We can probably observe it in optical polarization. Thanks. Yes, always
absolutely.
a guess.
There will be so many alerts that you cannot imagine. I mean, because the next time will be in 80 years. So really people want to observe this before they die. So there are so many proposals already there, ready, and people literally ready to observe it because we want to observe this as soon as possible after the explosion. And especially from a spectroscopical point of view, it's very interesting to have all these lines in the very early stages. This is 22 days after, but having this, very close in time will be very important to understand more of the physics of the propagation of the shock. Yeah, sure.
Well, you know that here we have this. We're expanding in Skinacus, and it's still like a kind of a preferential channel, so we can, if you can trigger us also with some days of some days in advance, and we could observe it and see the polarization. Yes,
Absolutely.
in optical polarization. Okay, then thanks, Rocco. Again, it was very interesting.
Well, thank you very much for the invitation. It was a pleasure. See you soon.
See you. Then
Bye.
see you.
Bye.
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 Bye.